Good evening, everyone. I'm Srividya, and I'm part of Team Shakti. So today, as a part of our conference talk, we will be having Miss Anindita Banerjee, who is the head of Quantum Research Head and the Vice President at QNU Labs, and would be speaking about quantum safe solutions for cybersecurity. Dr. Anindita Banerjee received her PhD from JP Institute of Information Technology in Noida. And during her PhD, she was a visiting scholar at the University of Calgary and University of Brunswick in Canada. She was also an assistant professor in the Women's College of Engineering in Durgapur. Later, she joined as research associate in Boyce Institute at Kolkata, where she spearheaded the group leading to successful demonstration of a single photon experiment in 2016. She was awarded CSIR Pool Officer in 2016 and has published around 20 journal publications. She has co-authored a book on optical quantum computation and quantum communication published in SPI Spotlight series. She has also contributed in developing India's first quantum technology product in quantum key distribution and quantum random number generator. She and her team has demonstrated India's first quantum secure communication and data transfer using DPS, QKD, and 50 kilometers distance using underground fiber. Apart from her academics, she is an Alankar in Indian classical dance and performed nationally and internationally under Kadam production of Padma Shri. Over to you, Ms. Anindita.
Hello, everyone. Thank you for the kind introduction. So I welcome you all, particularly the bright, beautiful, and bold women leaders, future leaders, and aspirants to this presentation. So today's cryptography is actually a multidisciplinary field, providing a lot of scope, opportunities, and there is a requirement too. I'm working as a quantum research head in QNU Labs. QNU Labs is India's first quantum technology-based deep tech startup, focusing on quantum hardware like quantum key distribution system, quantum random number generator, and also develop solutions, quantum safe solutions around it, addressing the problems of present day state-of-art cryptography. So we leverage on quantum information to address these challenges. Recently, we have partnered with Amrita University's Center for Cybersecurity Systems and Networks. And we are very happy with that. And we believe that our collaboration will enable innovation and it will strengthen and enhance research capabilities at both our ends. I would like to thank the organizers for this wonderful conference and also for inviting me. So I will start my presentation. I will start my presentation by acknowledging the 75% women workforce in Bletchley Park during World War II. So prior to 1970s, the crypt analysis, as you can see, was more of a manual process, and much of it was performed by women. My next slide, I wanted to touch upon actually ancient cryptography and also draw an association of cryptography with women. So this is given by Lichika Vikalpa, which is an ancient art of secret writing written in a text in 4th century AD, based on a manuscript dating 4th century BC. The secret communication in Indian, great Indian epic Mahabharata and also in other ancient kingdoms can be linked to this text. So now we're talking about present cryptography. So in present cryptography, you have the famous cryptographic couple, Alice and Bob, where Alice will try to send a message to Bob secretly. So what will Alice need is a plain text, which is a message, and encryption algorithm, and an encryption key. So when you feed the key and the text into the algorithm, it gives you a cryptogram. And it travels to Bob. Now, there can be a hacker in between who has to break through the encrypted data. Another aspect is the key distribution, particularly sending the encryption key and the description key. So if there is a man in the middle who is in between that link, it can be a physical link or it can be a trusted courier. If he gets hold of that key, then the entire cryptography fails. So this is the famous key distribution problem. Earlier, it used to be, when I'm saying earlier, I mean ancient or medieval, they were all symmetric key cryptography, where the encryption decryption keys were same. But the problem lies when you have, so we talk about this when we discuss the modern cryptography. In modern cryptography, it is based on mathematical complexity. So in 1976, Diffie-Hellman published New Directions in Cryptography. He developed the idea of dual key, which gave the key distribution problem a pragmatic approach. Each user had two mutually inverse keys. Encryption key is published and decryption key is kept secret. And the most widely used public key cryptography is the RSA, which is based on the difficulty of factoring a product of two large prime numbers. Now, so I can say that the present day cryptography is as old as computers, which should be something around 70 to 75 years. And when this cryptography was designed, the adversarial model was based on computational security and on a classical computer. So whatever mathematical algorithm, if it is not solvable in real time, or the shelf life is not an issue, then it is considered secure. So that was a model we were working with. So we never thought about quantum adversary, and also about the information theoretic security, which is when the adversary has huge resource of time and space, and with computational power is actually an exponential advantage to the present day classical computation. So that type of security was not considered. So today, when we are on the verge of a new technology, which is quantum computing, so we have to revise our cryptographic primitives and the cryptographic techniques and the adversarial models, whether we have to make it secure from the quantum also or not, and how do we do it? So the challenges. The first challenge is, of course, the computational power, the increasing classical computational power. So the RSA 250, having 829 bits, was factored in February 2020, indicating that any encrypted data with anything less than 1024 bits RSA can be crashed. Now, if we talk about human ingenuity, or we talk about mathematical advances, then it has been in news that a famous German mathematician had cracked the RSA using less intractable, shortest vector problem. Now, the issue is not that whether or not the algorithm is true and how much truth lies in it, or what is the capability, how much of a threat it is. The issue is that this situation is getting frequent. The issue is whether the entire cryptographic structure getting challenged again and again, and the fear which it brings along. So these are practical issues. And as I mentioned earlier also, that these is becoming so frequent. So we should not take any step in haste. We have to think, it has to be well researched. So these are the challenges. Then, of course, quantum computing. Peter Shor showed that quantum computers could factor a large product of primes in polynomial time. Now, this was never thought about, in contrast to the best classical algorithm in a classical computer, which takes a sub-exponential time. So this was an exponential speed up. And if such a crypto-cracking quantum machine was to be developed, then the entire cryptographic structure would crumble. So this was a fear, this was a challenge, and very interesting. That's why a lot of developments are taking place in this direction. And you can see that there is a paper on how to factor 2048-bit RSA integers on a classical computer having 20 million noisy qubits. It will take only 8 hours. So the entire algorithm had been broken down into quantum circuits, and how much time these gates will take, all have been computed. And thereafter only this time has been estimated. So it is becoming realistic, right? Then we look at fiber tapping. Now, Ethernet and optical fiber tapping is nothing new and has been in public knowledge for a long time. Now, the optical fibers, I don't know why, but it is considered that they are very secure by certain organizations, maybe because of accessibility. But we study that, the physics behind implementation of a fiber tapping isn't very difficult. And when we are doing our quantum key distribution, which is based on carrying information in light, we are actually trying to do this kind of an attack on the quantum channel or the optical channel, and to see that how much of a disturbance it creates or how much information. Of course, in quantum regime, it is not possible to do such an attack, but we see the impact using different parameters. And in classical, it has been well studied, and though there are precautions, but still, one has to be very careful about it. So then we are talking about where is the threat? It is actually from the quantum computing capabilities, where you can crack the Diffie-Hellman, the discrete algorithms, and integer factoring can be done. And this includes algorithms like RSA, DSA, DH, electrical cryptography, and the security protocols that derive security based on these algorithms is also a challenge, is a big concern. Or any product or security system that rely on these algorithms is also a challenge. And why should we be concerned? Because they are almost everywhere, starting from secure software distribution to secure email, VPN, secure web browsing, digital signatures, key agreement protocols. So they are actually everywhere. And so it is not a quick transition to quantum safe, and it is a concern. So now let's look at ideal security. So what does an ideal security look like? So according to a mathematical principle, the adversary can have the entire crypto system. They can know about the encryption algorithm. They can have the cryptogram, but what they should not have is the key, encryption key. So that is the challenge, that the key should not fall into the hands of adversary. Rest everything can be known to them. So the security is as good as the secret key. Now, what should be the properties of the key? Key is a binary string of random numbers. The key should be random. Then, of course, the question comes, how much random? What is random? But let me not address these issues. Let us understand that the keys should not be reproducible, unpredictable, and they should be random in nature. The key should not be cloned. It means that today, if I'm able to send a key in encoding it in optics, then there is no way I can find out whether it has been cloned or not, or somebody has looked into or not, or monitored it or not. But in quantum mechanics, since I'm encoding the information on quantum properties, it is protected by a law of physics known as no cloning theorem. Then the key tampering should be detected. In quantum mechanics, what happens is, if you are monitoring a state, you are disturbing the state and it collapses according to the measurement. So any detection, tampering done on the quantum state, which is the key, is detectable. It gets monitored. So the quantum mechanics is ideal solution for doing a key transfer. So the advantages which the quantum information science brings is the information. So we say it's quantum information science, and it is bounded by the laws of quantum mechanics. So we give the adversary the power of physics. So anything which is possible according to the laws of physics, an adversary can use it as a tool to hack the system. And when we do security analysis of such a cryptography, we have to take care of all the information leakages which can happen because of different quantum attack models, and take that into the security framework. So, and the information is encoded on a single particle of light, which is, so these are photons, these are microscopic. The rules of physics for microscopic is quite different. So when we say microscopic, it is subatomic level kind of a size. And the photon is known as flying qubit. And photons are used for quantum communication, whether it be quantum internet, it is used for quantum random number generators also, or any kind of communication from point A to point B. Photons behave differently and follow different rules in the quantum world. Then no cloning theorem is a fundamental theorem in quantum mechanics. You cannot copy the state. Heisenberg's uncertainty tells you that if you try to monitor the state, it will cause disturbance and it can be monitored. Superposition principles is the inherent property of quantum mechanics, and it allows a state to be there in two particular possibilities or many particular possibilities. Then you have Bell inequality test. Then and there are other resources also, counterfactual, and then there are other principles, and based on different principles, different QKD protocols can be devised. Now, quantum key distribution enables secure, symmetric keys. This is very important. The keys generated by quantum key distribution are symmetric in nature, and hence these are well applicable for algorithms, encryption algorithms like one-time pad. So just imagine a combination of the information theoretic encryption algorithm like one-time pad combined with an information theoretic key distribution scheme like a quantum key distribution can give you a very secure, a very robust cryptographic structure. And QKD is resilient to any adversary with unlimited resources of space and time. Basically, it is resilient to any algorithm. You are not algorithm dependent. So that, and it gives you a long-term security. If I look at uncertainty principle, this is a thought experiment. So Alice and Bob, Alice is sending some electrons and it is passing through a metal wall with two small holes. And these two particles will interfere with each other, P1 and P2. So this is a classical probability curve. So when S2 is closed, I'm getting a bell curve like P1. When S1 is closed, then I'm getting a bell curve like P2. The addition of these two should be a classical probability curve. But what I'm observing is an interference pattern, which is a quantum signature. So let me put it very simply. If nobody is observing the state, I can see a quantum signature, or Bob can see a quantum signature. But if somebody is observing the state, it's trying to find out from which hole the electron had gone, then it is destroying the interference pattern, and I'm seeing a classical probability curve, a bell curve. So then Bob knows that somebody had perturbed the state, or somebody is looking into the state. So you see the laws are very simple. The law says if nobody is eavesdropping, there is no perturbation or no measurement, then it is secure. If somebody is trying to hack it, tap it, or put a probe to it, do some kind of a weak measurement, it cannot escape. It will disturb the state, and that can be monitored. So now how much disturbance, how much it can be monitored, what are the parameters we have to look into so that we can understand this kind of a disturbance is looked upon in and well studied in quantum key distribution. So I will not go into the maths, but let me just simply tell you the linearity of quantum mechanics. Actually, that is the main reason because of which you will not be able to clone a state, or you'll be able to copy a state. It will never give you, for example, if it is a state like ket0. In quantum mechanics, we write the state in direct notation, which is used in linear algebra. So this is a ket0 and ket0. Let this be an empty paper, and this is a state you want to copy into the paper. Quantum mechanics will not allow it to be reproduced if the state is an arbitrary quantum state. An arbitrary quantum state is a state which will have a certain probability to exist in all its possible states. For example, here you have A ket0 plus B ket1. So it has alpha A square probability to be in 0 state, B square probability to be in 1 state. So it exists in superposition. So basically, when you are looking at a state, you are collapsing the state into one of its possible states. And it is not possible to reproduce the arbitrary quantum state. So now what kind of a solution does quantum safe solution or quantum cryptography mean? So there are two solutions. One is a hardware approach, and the other is a software approach. Um, can anybody confirm that I'm audible, or because the silence is somewhere I feel I start getting lost?
Yes, we
Are you
hear
with me?
you.
Are
We
you
hear you.
Okay, great, great. So there are two solutions. One is the hardware approach, which comprises of two boxes. One is a sender box, other is a receiver box. Both will have optical units, electronic units, processing units, a lot of cryptographic primitives like hashing, the error correction codes will be there. So this is a hardware structure. So this provides you long-term security, and you are no longer dependent on algorithms. And even if your adversary has a quantum computer, still the coding which you have done with key distribution facilitated by quantum mechanics can be considered information theoretic secure, provided the implementation is secure, the implementation is scientifically correct. Okay. So now the second is software approach. In software approach, there are certain algorithms which cannot be cracked by a quantum computer. So we say them quantum resistant classical algorithms. These are called post-quantum cryptography. So there is a software approach, but it is not very easy to replace all the existing software algorithms with the PQC algorithms. It will have many factors, like you have to look into the security from classical point of view, from quantum point of view, or quantum random oracles you'll have to study. Then you'll have to study the implementation cost, and how are you going to implement this basically in network, and how the network is going to, what is the design of the network. So lot many things are there. It is not a simple implementation, and will take some 7 to 8 years, I think, to transit from present cryptography to quantum resistant cryptography. So at CUNY Labs, we we started our company, we started with quantum key distribution experiment. So this has been a journey from theory to an experimental bench, and then converging that to a product. And each of them had come with its own challenges. When you're working in an industry, so the approach is different. So you'll have to come up with protocols which will give a commercial advantage. So it should have a higher throughput. It should be able to cover long distances. So you'll have to study which kind of a protocol will be suiting the requirement. For that, you have to understand what is the right source you will be taking, whether it is the weak coherent source. Today, commercially, weak coherent sources are used for quantum key distribution, or it is a single photon source, or it is an entangled source. The security principles I mentioned earlier are also different. Based upon the type of protocol, security principles are applied. Encoding, there are different methods of doing encoding. What is the best for the implementation, where you will be getting a lesser QBER. Many things needs to be studied to actually decide on what type of encoding can be done. There are two different protocols. For example, take BB84 protocol. In BB84 protocol, you can encode the quantum state both using polarization and phase. So a lot of study has to be done to understand, to select the right encoding. Then based on the detection, what type of detection you want to use, whether it is a single photon detector or it is a homodyne detection. Then of course, range, you want to do a ground to ground, or you want to do a satellite to satellite, or ground to satellite. So lot many things needs to be understood to finally come up with a right protocol for your requirement. So what does a quantum key distribution configuration looks like? So you have Alice and Bob systems separated by two channels. One is a quantum channel, which will be carrying your quantum states or photons, and the other is a classical channel. It can be optical fiber, it can be an Ethernet link, and of course, you can also combine these two channels. What we do in the classical channel is actually sending the clock information. Because you see, even though the Alice and Bob can be kilometers apart, there has to be a picosecond synchronization between them. There has to be a very good error correction code running in these modules. So lot many post-processing things like privacy amplification, error correction, authentication, all these algorithms are run on the classical channel. And on the quantum channel, only photons or quantum states are sent. QKD algorithm, so as I mentioned, you select the right algorithm, then you have a quantum transmission stage. Depending upon the algorithm or the protocol, you have a sifting stage, then you correct the errors, you analyze the security, the source parameters, what is the leakage, then you come up with a compression factor, and then you apply hashing to it to secure it or to make it uniform. And then with a particular negligible probability, which is known as security parameter, you generate the final secure keys. What we do at QNU is a different distributed phase reference QKD protocol, where you have the source and the attenuator. You can consider it as a quantum source. Then I'm modulating the photon, single photons, using based on the random numbers which are generated. So this RNG can be a TRNG or it can be a QRNG. So I'm encoding the photons using this random number generator. Encoding can be again on frequency, time, polarization of phase. Then I'm sending them through the quantum channel, and then it is decoded. So I can say it's a source generator, encoding, transmission, decoding, and detection. So this is the optical layer. And apart from that, whatever happens is actually classical cryptography. So after you have detected the states, you have to do, so this is the Alice and Bob. I should mention that quantum key distribution only solves your key distribution problem. It doesn't solve authentication. So the Alice and Bob has to be prior authenticated using state-of-art algorithms, right? And thereafter, you do the key transmission is done. Then after the detection, you do error correction, privacy amplification, reconciliation, and finally, you will be generating secure symmetric keys at both the ends. If the error rate is high, then somebody is eavesdropping and we abort it. In that case, keys are not generated. Now, these are encryptors. So if you want to have a cryptographic message between them, then there is a technique of how the keys are never sent through the channel. They are generated at Alice and Bob, and they use these keys to do the encryption and decryption. So this is one of the communication which we had performed in our lab. So these are the two systems, Alice and Bob. They are connected by a clock channel, which is a classical channel, and the post-processing is done through an Ethernet link. And then there is a quantum channel for quantum transmission. Once the keys are generated, the router requests the key from the Alice. If Alice has to send a message to Bob, it will encrypt the Alice's message with the key and send the cryptogram through the channel and also a reference ID. At Bob, the reference ID is used by Bob to find out the corresponding secure keys. It will take the key from here, apply the decryption algorithm, and then obtain the final message. So we have performed this activity in our lab and also in other labs and in critical infrastructures. We have demonstrated them, and we'll be happy to give you a demo sometime. And after the keys are generated, one more thing is the keys which will be used for encryption has to satisfy the randomness property. So we test the keys in NIST test suite, in Die-Hard, in ENT, in TO1, and to finally say that the keys are good enough to be used for cryptographic purposes. Some of these works are published in these papers. If you're interested, you can go through them. And finally, this is a demonstration we had performed for some critical customers, and where we have taken the keys and we have done video conferencing and also encoded voice messages and sent it from one node to the other node. Now, QKD does not, we say that, it is bounded by some distance. You cannot make it thousands of kilometers. Of course not, because Alice and Bob, if you're doing fiber-based QKD, you are limited to about 150 kilometers. If you use some other technology like a superior single photon detector or ultra low loss fiber, you can still go to 400 kilometers, but not beyond. For higher distances, you have to use satellite QKD. And this QKD is always between two nodes, Alice and Bob. So there is a particular way in which you can extend it to multiple nodes. This is what China has done with the Beijing satellite. We call them as trusted nodes, and the keys are generated between Alice and Bob, and then it travels to C using a one-time pad. So if you're interested again, I can explain that in person or send a small note for you to understand how this really works. I will not go into much detail. Random numbers, of course, we know it has to be unpredictable and uniform. So classically, there is no way you can generate an unpredictable numbers. If you toss a coin today, earlier it was considered random, but today we know that it can be simulated, right? Similarly, the chaotic lasers or QRNGs, they are all are complicated environments, and once you can solve them, you can easily predict the occurrences. But quantum mechanics is inherently random. You will never be able to predict the outcome. So that is why it guarantees the predictability. And of course, if the algorithm or if the random number generator is such that it will generate uniform distribution of bits, then you have a very good case. The random number generators which are used today for cryptographic activities are basically PRNGs, which is algorithm based, and they suffer from various drawbacks. For example, existence of backdoor and weak entropy, repeatability of seed. And true random number generators, if it depends upon classical physics, it is known as a TRNG. If it depends upon quantum physics, we call it QRNG. At QNew, we have developed a optical QRNG. We have progressed from generating 1 Mbps to today we are generating 100 Mbps. We have also come out with enhanced hash DRBG, where you can actually take the entropy from a quantum source and then you expand it and then generate higher throughput. So I will not. I'm running out of time. Can I take 5 minutes more, or do you want me to close in a minute? All right, I'll just go fast. If you look at a quantum random number generator, it basically has 3 units. One is the state preparation, second is the data acquisition, and third is the conditioning. The idea behind the slide is that now the international bodies are actually working on standardization of these kind of quantum random number generators and QKD, and there exists several standardization white papers and they have come out with different rules, how to evaluate a quantum technology product. So this is a scheme that we work on, and I think I have already mentioned that we have this. Okay, I can send the paper on this work of how we are generating using time of arrival QRNG. The result, the random numbers generated from the optical QRNG, we have evaluated using NIST and other testing platforms, and they have passed almost all. And this is the last slide. The last slide, we wanted to convey that the vision of our company is to provide a quantum layer of security to the existing classical primitives or classical cryptography. So this is what we are working up and trying to come out with different solutions using the products we have. So any questions, any quick questions I can take? I'm sorry for exceeding my time. Hello? I'm not able to hear anybody. Hello?
Thank you, Anindita. That was an excellent talk. Just waiting on Srividya to come on. We do have several questions.
Yeah, I'll be happy to take them. If you can send me by mail or I can be of any help with the questions, I'll be more than willing. I can see some questions in the chat. Do you want me to?
Yes, if you can just address them, that would be great.
Okay.
Should I read them out to you, ma'am?
Yeah, I mean, either way, I can always type it here if.
Yeah, I can quickly tell it out, so maybe you can speak. Maybe that's faster. So the first question: what are the challenges faced by QKD?
Distance, of course, and the throughput, the key rate. These are the basic challenges because the signal is so weak that it is very difficult to get a good rate at long distances. So key rate and distance is a challenge.
Second question: how can one begin a career in quantum computing and specialize in quantum cryptography?
Okay, these are different areas. Quantum cryptography is where you have to understand or study, quantum optics, quantum information science, quantum security models, secure communication protocols are different. And when you delve into these protocols, you'll have to understand the security framework. So this is a different study, though both the subjects are based on quantum information, but it is difficult to jump from one to the other.
Thank you, Anindita. There are some questions. So from the question A, some people have some questions. So the first would be, how effective would it be if we implement quantum security protocols and existing cloud machines?
So we are working on that, how to make the cloud machines secure, quantum secure. So there is something called quantum security hardware module. So this is, when you say cloud, it is data at rest. So what we are addressing is data in motion. So to address the data at rest, making it quantum safe would require encoding of the data which is there in the station using quantum random numbers, or when you're transferring the information from one station to the other station, then you'll have to use QKD so that you don't have to carry the keys or the data from one station to the other station. So there are certain a thought process going on in this direction, and we have started thinking on quantum security hardware module as a solution to this.
Thank you. And another question is that, is there any way to use entangled qubits for each cloud?
So entangled qubits, when you say it is, we are doing a quantum communication. So in entangled qubits means there are photons which has to travel from one station to the other. So wherever there is a quantum key distribution, the source can be, it can be a single photon source, or it can be a quantum entangled source also. And if you're talking about some computation, which is done on the cloud using entangled qubits, then of course it is there is a way, and it is more advantageous.
And another question is that, is there any opportunities for the study of energy dissipation levels in quantum security products?
Is there an opportunity for the study of energy dissipation levels?
Yeah.
Side channel. Do you indicate side channel attacks?
Energy dissipation levels in quantum security products.
Okay, so when we talk about quantum products, particularly if we say quantum key distribution and quantum random number generators, then the standardization bodies talks about different dissipations which are possible, or the system has to be made resistant to the different side channels, differential power analysis attacks, and so many other attacks are there. And they are more of classical in nature. When you're talking about energy levels, optical energy level, so it's very weak. It is not possible. And if I'm saying it is, yeah, I mean, if I'm trying to hack an optical channel, then I will be using a dissipation method, which is called beam splitter attack. But that is a different thinking altogether. And I think here you mean to say the side channel attacks. So of course, whatever is implied in classical cryptography applies here also. A lot of processing is happening inside the system.
And our last question is, does quantum node pair have fixed number of entangled?
Can you please come again?
Our last question is, does quantum node pair have fixed number of entangled qubits?
So now you're trying to think this in terms of quantum computing, where you have fixed number of qubits, right? But here, what happens in quantum key distribution is, or in quantum nodes is, you have, okay, now just think that there is a laser in one of the nodes. The laser emits millions of photons in one particular pulse. There is an optical pulse with 50% duty cycle. Say the on time is around 500 picosecond. So I'm running the laser at 1 gig rate. One optical pulse, 50% duty cycle. You have a 500 nanosecond pulse there, and it has some 20 million photons inside it. I will be reducing it to an average photon number of 0.1. So that is a level. It is in picowatts level I'm talking about. And it is not possible to think that, it can be quantified that these many photons will be there or not. It is not possible. But you can think, if you're talking about quantum computing or a quantum computer, then of course this question is valid.
Thank you, Anindita, for giving such an informative and enjoyable session on quantum security communication and QKD protocols. Thank you.
Thank you.